Hi guys, welcome to our YouTube channel. My name is Martinji. I am a student of Sri Venkateswara College of Engineering, Bangalore, USA. 1VE 23 EC056. Subject: Applied Physics for Triple E Stream. Section: Honda. Subject code: BPHYE 202. Topic: Relation between Fermi energy and energy gap in intrinsic semiconductors. Introduction: Intrinsic semiconductors are materials with a balanced number of electrons and holes. The Fermi energy in an intrinsic semiconductor lies midway between the valence and conduction bands. The energy gap in intrinsic semiconductors determines the conductivity and electron-hole pair generation. Fermi energy. The Fermi energy represents the highest energy level that electrons can occupy at absolute zero. In an intrinsic semiconductor, the Fermi energy level is located at the center of the band gap. It serves as a reference point for determining the probability of finding an electron at a specific energy level. Energy gap. The energy gap is the energy difference between the valence band and the conduction band. In intrinsic semiconductors, the energy gap is typically in the range of 0.7 to 1.1 electron volt. The energy gap directly influences the electrical properties of the semiconductor. Relationship: The Fermi energy level in an intrinsic semiconductor lies exactly halfway between the valence and conduction bands. The energy gap determines the minimum energy required to excite an electron from the valence band to the conduction band. At absolute zero, the Fermi energy is at the midpoint, and all states below it are filled while those above it are empty. Semiconductor behavior: When a semiconductor is at thermal equilibrium, the Fermi energy remains constant. Changes in temperature or doping levels can shift the position of the Fermi energy. The energy gap determines the conductivity of the semiconductor at different temperatures. Band structure: The bond structure of an intrinsic semiconductor shows the energy levels available to electrons and holes. The Fermi level serves as a reference point for determining the probability of electron occupation in this level. The energy gap sets the limit for the energy range in which electrons can move freely. Electron hole generation. In an intrinsic semiconductor, electron hole pairs can be generated by thermal excitation or optical processes. The energy gap plays a crucial role in determining the energy of the generated electrons hole pairs. The Fermi energy level affects the distributions of these electrons holes pairs within the semiconductor. Carrier concentration. The carrier concentration in an intrinsic semiconductor is determined by the position of the Fermi energy. At equilibrium, the number of electrons equals the number of holes, maintaining charge neutrality. Changes in temperature or doping alter the carrier concentration by shifting the Fermi level. Conductivity. The conductivity of an intrinsic semiconductor is influenced by the position of the Fermi energy within the band gap. The absolute zero, the Fermi energy, is the highest energy level occupied by electrons. Increasing the temperature excites electrons across the band gap, leading the increasing conductivity. Optoelectronic application. The relationship between the Fermi energy and the energy gap is crucial in optoelectronic devices. Photovoltaic cells and light-emitting diodes utilize this relationship to control electron-hole pair generation. By manipulating the Fermi energy and energy gap, the efficiency of these devices can be optimized. Equilibrium condition. In equilibrium, the rate of electron hole generation equals the rate of combination in an intrinsic semiconductor. The Fermi energy remains constant under equilibrium conditions. Changes in external factors can disrupt this equilibrium and alter the position of the Fermi energy. Temperature dependence. The position of the Fermi energy in an intrinsic semiconductor shifts with temperature changes. Higher temperatures lead to increased electrons excitation across the band gap. This temperature dependence affects the conductivity and carrier concentration in the semiconductor. Doping effect. Doping introduces impurities into the semiconductor, shifting the position of the Fermi energy. N-type doping increases the electron concentration, lowering the Fermi level. P-type doping increases the hole concentration, raising the Fermi level. Minority carrier lifetime. The relationship between the Fermi energy and the energy gap influences the minority carrier's lifetime in semiconductor. Higher energy gaps result in longer minority carriers lifetimes. The position of the Fermi energy affects the recombination rate of minority carriers. Band to band transition. Band to band transition in an intrinsic semiconductor involves electrons moving from the valence band to the conduction band. The energy gap determines the minimum energy required for these transitions to occur. The Fermi energy level provides a reference point for analyzing the energy states involved in these transitions. Agar combination, recombination. Agar recombination is the process where the energy released during recombination is transferred to a third carrier. The Fermi energy level influences the likelihood of agar recombination occurring in an intrinsic semiconductor. Higher Fermi energy levels increases the probability of agar recombination. Shortcut defects. Shortcut defects are vacancies in an otherwise perfect crystal lattice. The position of the Fermi energy affects the formation and stability of Schottky defects in semiconductor. Energy gap variation can lead to changes in, in the defect concentration within the semiconductor. Quantum efficiency. The quantum efficiency of a semiconductor device is influenced by the relationship between the Fermi energy and the energy gap. Optimizing this relationship enhances the device performs in applications such as photodetectors and solar cells. Controlling the position of the Fermi energy relative to the band gap is essential for maximizing quantum efficiency. Conclusion. The Fermi energy and energy gap in intrinsic semiconductors play critical roles in determining their electronic properties. The positions of the Fermi energy affects carrier concentration, conductivity, and electron hole pair generation. Understanding the relationship between these parameters is essential for designing and optimizing semiconductor device. Thank you guys.